Okay, let's continue our discussion. So in the last video, we have discussed different types of stress, means longitudinal stress, shear stress, and hydraulic stress, and corresponding strengths in those cases. Now we are going to discuss Hooke's law. So what happens for a small deformation, means up to certain limit, most of the materials follow this thing. Stress is directly proportional to the strain produced in the body. Or we can say, if we want to remove this proportionality sign, we can write stress equals to something proportionality constant into strain, and this proportionality constant is known as modulus of elasticity. Okay, so in symbolic form we can write, generally we represent this stress with Greek alphabet sigma, and this is small k and this is epsilon for strain. So this is Hooke's law, and most of the materials follow this thing up to certain extent. Now we are going to check a specific case, and we want to draw the stress strain curve. So let's say here we have a metallic wire. Let's say this is a copper wire, and we have applied an external force. This force is trying to stretch, let's say Fext. This force is trying to stretch this wire. So how this wire will behave now? Here it has been fixed. Okay. So initially, what happens? When we start applying this external force, there will be corresponding restoring force in this wire or in this material here, and that restoring force, let's write it FRES. This restoring force per unit this cross sectional area will be stress produced in this wire. We have discussed already longitudinal stress. Now in that case there will be corresponding strains, means there will be fractional change in its length. So there will be relation of the stress produced and this strain also, and that relation we are going to plot. So let's take it first, how this wire is going to behave. So when we start applying this force with increasing force, or we can say with increasing restoring force, and correspondingly with increasing stress, there will be a strain in this wire. So initially what happens, let's start with some point, something O, and we are applying this external force, or increasing, most precisely increasing this external force, and this external force is going to give rise in stress, as there will be restoring force here. So with increasing external force there will be increase in stress also. So initially when this stress increases up to certain point, let's say up to certain point A, this stress increases and there will be increase in strain also. So up to point A, this stress and strain behaves linearly, means there will be linear correspondence, means there will be obey of Hooke's law, and up to this limit there will be linear dependence of stress and strain to each other. Now beyond this, let's say up to a certain point B, now this is non-linear relation, means stress is not now directly proportional to strain. Up to here it is directly proportional, but if we apply further this increasing external force, that will result increasing stress, but now the relation of this stress and strain is non-linear. So from here this material is not behaving or not obeying Hooke's law. Then from B to, let's say, next point up to D, from here to here there will be large strain, and up to D it is happening in this way. So again the plot will be non-linear here, and Hooke's law, no, this material is not obeying Hooke's law now. So this material is obeying Hooke's law up to here only, here only, up to A, and this A we call proportional limit. And from B to D, now this region is non-elastic region, or we can say this region is the region where this material is behaving like plastic. Now, up to B, this material is going back to its original shape or initial shape. But after B, and we have removed this external force now, then this wire is coming back, but it is not coming back to its original length here, but it will lie somewhere here, which means there will be some change in length. And that difference, we can say, that is a kind of permanent shape, means it is now not behaving like a elastic material. Okay. After D, if we are reducing this stress, means after D, up to here we were increasing this external force and hence we were increasing this stress. Initially, this stress and strain were behaving linear relation, and then it came to a point where from where it is behaving like non-linear. Still, it has the ability to come back to its initial shape if we remove this external force. So up to point B, this material is behaving like elastic material, and up to point A, which is proportionality limit, up to point A, this material is behaving or obeying Hooke's law, means there will be linear relation between stress and strain. But beyond B, now this is plastic region, and anywhere after this point, if we are removing this external force or this stress, this material is not going to get its initial shape again. There will be some change in shape, and that amount we can call this is permanent shape in the material. And further, beyond this point D, now even if reducing this stress correspondingly, there will be increase in strain, and at point E, this material breaks. So we call this point as fracture point. This point is fracture point. Here we have. So when we are increasing this stress, correspondingly strain is going to increase. And look, up to point A, it is following Hooke's law. It is, look, this graph is linear, a straight line, or we can say there is linear relation between stress and strain. But beyond A, up to point B, you can see here, up to point B, look, again from point B, it is coming back to its original shape. So up to point B, this material is behaving like elastic material. So this is up to point B, elastic region. But beyond point B, this material is now not going back to its original shape, even after we are reducing this uh, stress to zero. So this is all plastic region. And beyond this is graph is coming down, means stress is being reduced. Again, there is increase in strain here up to fracture point. So if this D and E are close, the material is brittle. If this D and E are far away, then the material is ductile. And such material we use in making wires. Okay, so this point A is proportional limit. Up to here, the stress is directly proportional to a strain. Beyond this, now it is not directly proportional, but up to point B, which is yield point, or this stress is called yield stress. This sigma y, yield stress. Okay, so up to here, it can get back to its original shape, but beyond this, it is not coming back. Okay, so this change here, let's say from point C, we have removed this external force, and this material is trying to get back its original shape, but it won't come back to its original shape. There will be some shift, and this is permanent shift. It is not coming back to its original shape now. Okay, and this D is actually ultimate point, means this D is kind of, you can say this sigma u is ultimate tensile strength. Now, there are some materials which do not obey Hooke's law. Let's take rubber. So, rubber, what happens? We can stretch rubber up to a greater extent. Means rubber has high elasticity. And let's take one more example for which we have a plot here. Aorta. Aorta is the largest artery which takes blood from the heart to This aorta is like rubber type material, you can say. And here, look, this is stress and this is strain. And now you can see this is almost non-linear. If we are just marking up to here or something here, linear up to certain extent, but in the most part, you can see it is non-linear. So in that case, we can say this iota is not obeying Hooke's law, but it has, look, it has high tensile strength here. It has high ability to get back to its original shape, even if higher stress, look here, 10 to the power 6 Newton per square meter. You can think that the force on 1 meter square area here is 10 to the power 6 Newton force. This much stress here it is holding. And then there will be a strain of 1. So it has high stress to strain ability, or you can say high range of elasticity. Now, it has not proper plastic region. So such materials like rubber aorta, which has high ability to get stressed or high range of elasticity, such materials we call elastomers. So this is all for this video. In the next video, we will continue with the propensity constant here we have discussed were here, modulus of elasticity.